Today, what I'd like to do is a strange example. We are so used to examples that are not so strange, that are things that are we just kind of take for granted, that examples like what I'm about to show you just are completely unexpected. But it does illustrate that when doing more theoretical math, as you may have to if you need to study something more advanced, for example, like artificial intelligence or something like that, there are unexpected things that happen if you think about things too simplistically. So that's the main lesson for this example, is that strange things can happen. And you know, maybe you already know in math that strange things often happen when you use piecewise functions, and that's going to be the case here. Our function is going to equal e to the negative 1 over x squared, which you could also write as e to the negative x to the negative 2, if x is non-zero. And how about 0 if x does equal 0? I would have to define it separately when x is 0, because in this formula up here, if you plug in x equals 0, you'd be dividing by 0. We don't want to do that. We can ask and try to answer questions like, what's the Taylor series for this function? Perhaps most interesting at 0. Centered at, say, a equals 0, our usual thing to center a Taylor series at. So we're going to try to answer that question. We could also ask and try to answer the question, what is the interval of convergence? For e to the x, we know the interval of convergence for the Taylor series for e to the x is the entire real number line. Does that happen with this strange function? What is the interval of convergence? And even more importantly, does this Taylor series for this function converge to this function on the interval of convergence? Does it converge to the function? And remember, that is an issue. And by the way, I might test you on these kinds of things that we're talking about with this example, maybe in true-false questions, especially the answers that we obtain. Okay. It takes proof. Even if you got a series like for e to the x that converges for all x using the ratio test, for example, it's not completely obvious that it converges to e to the x itself, though we did see that. We did, in fact, prove that about a week ago, maybe. We proved using that error-bound formula for Taylor series that it converges to e to the x. Well, let's not assume right away that it converges to this function. What is the Taylor series for this function centered at a equals 0, also called the Laurent series? Let me give it a different name. Let me call it p sub infinity of x, because I'm purposely trying to say maybe it equals this function, maybe it doesn't. The general formula is to take f of 0, add on f prime of 0 times x, then f double prime of 0 over 2 factorial times x squared, then f triple prime of 0 over 3 factorial times x cubed, etc. So I need to figure out what f of 0 is, what f prime of 0 is, what f double prime of 0 is, etc. Certainly f of 0 is 0. This fact right there is enough to imply f of 0 is 0. And therefore, the first term here is 0. But what about the other terms? I got to take the derivative. Being a piecewise function, maybe it's strange. Maybe the derivatives don't exist. Maybe this function is not differentiable at 0. That's not so clear. Certainly the function is differentiable when x is non-zero. If x is not equal to 0, I can certainly differentiate this function in the ordinary way, because I would not be dividing by 0. Think about it. I could use the chain rule, right? Because the inside function is negative x to the negative 2. The derivative is going to be this expression, e to the negative x to the negative 2, times the derivative of the inside function, the derivative of negative x to the negative 2, will be positive 2x to the negative 3. So you could write the answer as, say, 2e to the negative x squared, negative x to the negative 2 over, I can take the x to the negative 3 and put it as a positive x to the 3 in the top, or in the bottom, x to the positive 3. So that's certainly the derivative when x is non-zero. But what if x equals 0? You can't use this formula to figure out what f prime of 0 is. That would not be allowed. I mean, you might think you could intuitively just let x go to 0 in this formula to figure out f prime of 0, take a limit. It does turn out to give you the right answer, but it's not always guaranteed. So you have to be careful in general. In reality, you need to go back to the definition of the derivative. Definition of the derivative from Calc 1. Derivative. Can't spell today. Definition of the derivative. Chapter 2, way back in late September, if you took Calc 1 last fall. F prime of 0 is, by definition, a limit as h goes to 0 of one of those difference quotients that give you slopes of secant lines. In this case, the value of x that's being plugged in is 0, so it would be f of 0 plus h minus f of 0 divided by h. You technically have to think about this limit to really figure out f prime of 0. You can't figure out f prime when x is non-zero and then let x go to 0. Like I said, it will give you the right answer in this case, but there could be examples where it doesn't. In fact, I know of examples. I might even show you one on Friday. F of 0, we already know is 0. This is a 0 here. So this does simplify to the limit as h goes to 0 of f of 0 plus h, which is f of h, divided by h. Now remember, when you take limits, technically speaking, it doesn't matter what happens to this function at h equals 0. You look at this expression, when h equals 0, it's technically undefined because you'd be dividing by 0, which you can't do. But that doesn't matter. I'm just letting h approach 0 without actually equaling 0. Maybe that limit will still exist. Plug in the function. When h is non-zero, I plug in the original formula up here. Replace x with h, e to the negative 1 over h squared, all over h. Now the temptation is to think, oh, I guess maybe I have to use Lhopitals Rule. Remember, when you use your Lhopitals Rule, you have to check whether the fraction involved there is indeterminate or not. Is it 0 over 0 or infinity over infinity? What are the top and the bottom approaching as h approaches 0? Certainly the bottom is approaching 0. Actually, the top is approaching 0 as well. Think about it intuitively. If h is really, really small, close to 0, but not equal to 0, like 0.01, for example. If h is 0.01, h squared would be 0.0001, 1/10,000th. This would be e to the negative 10,000 power, really tiny. The top is definitely going to 0. This is a 0 over 0 indeterminate form. Not indeterminate, but indeterminate is the official way to say that. And so we could try to use Lhopitals Rule. Let's see what happens if we do. Remember that with Lhopitals Rule, you take the derivative of the top and the bottom individually. Do not use the quotient rule. We're not differentiating the fraction. We're differentiating the numerator and the denominator individually and making a new fraction. The derivative of h is simple, that's 1. The derivative of that, hey, that's the same as the derivative of the original function, except with an h. It's this, or that. 2e to the negative h to the negative 2 divided by h cubed. All over 1, which I could just write as a simpler limit. Limit as h goes to 0 of 2e to the negative, I'll write it as 1 over h squared again, divided by h cubed. What have we gained? Nothing. It got worse. That doesn't mean the Lhopitals rule is wrong. It just means it's not helpful here. And if you tried using it again, it would be even worse. So what do we do? You might wonder whether this limit really does exist or not. Let's see if we can use Mathematica to check it. Before we think about the derivative here, let's also just get a little intuition about the function itself. So here it is in Mathematica. Notice I did use effectively curly braces here, although it's squarish looking. You can find that in the palette under typesetting. It's this button right there. So there's the function. Before we actually think about the derivative, let's think about the function values, and let's also maybe make some graphs. Like, what is f of 1? What is f of 0.1? What is f of 0.01? I got an error. X negative 10,000 is too small to represent it as a normalized machine number. Precision may be lost. Yeah, actually precision is lost right there. It says f of 0.01 is 0. That's technically wrong. It is very, very close to 0. In fact, f of 0.1 is even very, very close to 0. Look at that, 3.7 times 10 to the negative 44 power. Microscopically close to 0, but not equal to 0. Why is that happening? Well, think about 0.1. If 0.1 squared, that's 0.01. 1 over that would be e to the negative 100. This number right here is effectively e to the negative 100. Yep. Actually, you can force Mathematica to give you more decimal places of accuracy, even in this case, by using fractions instead of decimals. And I'm putting it in the n function, and I want to see 100 significant digits here. I'm also going to plug in 1 over 1,000 and 1 over 10,000. What happens? Something kind of mind-blowing. This big long thing times 10 to the negative 4,343 when the input is 0.01. This long thing times 10 to the negative 434,295 when you plug in 0.001. And when you plug in 0.0001, it's 6.45 times 10 to the negative 43,429,449. You've never seen such a small non-zero number in your life until right now. Yeah. I mean, I could keep going smaller. Wow. This function gets really, really close to 0 without actually equaling 0. Let's confirm that with a plot. This first plot, I'm plotting it, x going from negative 100 to 100. Here's what it looks like. But you've never seen a graph look like that before. Let's zoom in closer to x equals 0, negative 10 to 10. Zoom in even closer, how about negative 1 to 1? The graph is super flat here near 0. Does that happen as I go in even closer? Yep. And if I go in even closer, it's going to get even more extreme. So extreme, in fact, well, first of all, you've got numbers that are on the order of 10 to the negative 63 here. Secondly, it looks like now that the graph has corners in it. Looks like it's not differentiable anymore. That's deceiving, actually. It is differentiable. Those are not corners. It's Mathematica's approximation to the graph, and it goes down so far close to 0 that it makes this graph look like it has corners, even though it really doesn't. F prime of 0.1 does exist, but it's a very small number. And f prime of 0.0999 is also very small and a similar kind of order. I could go even smaller with my inputs. Go even closer and it's even more pronounced. Look, 10 to the negative 250 power. Crazy. F prime of x does equal this, and Mathematica does seem to be saying f prime of 0 is 0, though I'm not trusting Mathematica's algorithm there. Should I trust it if I plug in 0 here? Not necessarily. It's saying f prime of 0 is 0, but I shouldn't necessarily trust that. I really should try to prove that this limit is 0. Is there a way to do that? Lhopitals rule wasn't working. There is, but it's kind of subtle. I think it's worthwhile to teach you about. We're trying to prove this limit is 0. Let's think about series. But I'm about to write down a series that's not technically a Taylor series, and not even technically a power series in the usual sense of the word. Remember, e to the z power, where z is any number, actually either real or complex, is 1 plus z squared over 2 factorial plus z cubed over 3 factorial, etc. That works for any number z, any number. 1 over h squared is a number. I could replace z with 1 over h squared, as long as h is not 0. Avoid h is 0, because then you'd be dividing by 0. Replace each z with 1 over h squared. Why not negative 1 over h squared? Well, I'm coming to that later. Every z you see gets replaced with 1 over h squared. And if you're careful, you'll see this is what you get. That is a true equation as long as h is non-zero. Notice that all the terms, when h is non-zero, are positive. Question? I said I'm purposely avoiding the negative sign at the moment. Yeah, I will come back to that. Notice that all these terms are positive. So, therefore, e to the 1 over h squared, since it's made up of an infinite sum of a bunch of positive things, would be greater than or equal to any one of them. For example, greater than or equal to 1, also greater than or equal to 1 over h squared. In fact, it would be greater than or equal to any finite sum of these. I'm purposely picking the 1 over h squared because I have something else. I'm trying to prove this, and that's going to be the thing that's helpful. Now let's go back to e to the negative 1 over h squared. Oops. E to the negative 1 over h squared is the same thing as 1 over e to the 1 over h squared. If e to the 1 over h squared is greater than or equal to this, that means 1 over that is less than or equal to the reciprocal of 1 over h squared, which is just h squared itself. Does that make sense? Say it again. Let me go through the whole argument again. Listen carefully. So e to the z is this expression, no matter what z is. I can replace z with any number. How about 1 over h squared? This is going to be true as long as I'm not dividing by 0. These are all positive terms that are being added. E to the 1 over h squared is bigger than any individual one of them. For example, 1 over h squared for all h that are not 0. And therefore, if I take the reciprocal of both sides effectively, e to the negative 1 over h squared is going to be less than or equal to the reciprocal of this, which is h squared, for all h not equal to 0. What was my goal? My goal is to try to figure out this limit and show, like Mathematica predicts, that it equals 0, in fact. Notice I'm dividing by h in that fraction. This is going to be true for all h, technically, that are positive, because if h were negative, it switches the sign of the inequality. You can write down a similar kind of inequality when h is negative, but it's not the exact same inequality. Let's just worry about the case where h is positive. How is this helpful? The function whose limit I'm trying to show is 0 is between 0 itself and h itself for all positive values of h. It's squeezed between them. 0, imagine a graph. 0, h, and this function, somewhere below, somewhere between them, e to the negative 1 over h squared over h. Both of these functions have a limit of 0 as h goes to 0. Therefore, this one, because it's between them, is squeezed down towards 0 as well. In fact, it's called the squeeze theorem. That is a true theorem name, squeeze theorem. Is enough to say that since both of these go to 0 as h goes to 0, this one does as well. Technically speaking, I'm only letting h go to 0 from the right when I think about these inequalities. But a similar set of inequalities would also prove this limit is 0 as if h approaches 0 from the left. But remember, this thing was f prime of 0. So effectively, this is an almost proof that f prime of 0 is 0. To finish it, I have to let h approach 0 from the left as well. I have to, again, a different set of inequalities. So f prime of 0 is 0. You can also prove f double prime of 0 is 0, and f triple prime of 0 is 0, and f quadruple prime of 0 is 0. Mathematica says they're all 0. Zero, 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 and the zeros do keep going forever. What does this mean? Why was I doing this? Go back up here. I shouldn't stop there, although in reality I can. All those derivatives are 0. You got a bunch of zeros. It equals 0 for all x. Wait a minute. This function's only 0 when x is 0. It's really, really close to 0 when x is not 0, but close to 0, but not equal to 0. This function only equals its Taylor series at one point, when x is 0. Nowhere else. The series, the interval of convergence for this series is all x, because it's not really even a series in a sense. This definitely converges no matter what x is. But it only equals this function at one point. It does not converge to the function except at the trivial point x equals 0. They're really, really close together when x is close to 0, but they're not equal to each other. Does that blow your mind? It blew my mind when I first learned this. Here's something even stranger, perhaps. If you think about expanding this thing using the Taylor series for e to the z, like I did here, I could expand e to the negative 1 over x squared, not as a Taylor series, but as a series called a Laurent series. Laurent was French. It's probably more like Laurent or something, I suppose. All English speakers seem to say Laurent when they say this. Laurent series you can write this original function when x is non-zero as a series using this one. It's the same thing as this one, except every other one's a minus sign. 1 minus 1 over h squared plus 1 over 2 factorial h to the fourth minus 1 over 3 factorial h to the sixth, etc. Oops, I meant to put x's, sorry. Though that's true if x is non-zero. However, if you graph the partial sums of these, any finite partial sum here definitely does not equal this, and even has a vertical asymptote at 0, even though this function is really, really close to 0 when x is close to 0. It's weird. Here's an animation. Oh, wrong file. This one. This is a partial sum. I labeled it L because that's in honor of Laurent. Here, for example, is the 10th partial sum. Written in kind of a strange order. And here are graphs of the partial sums as the number of terms in the partial sums get bigger and bigger. So the red graph is our original function. The blue graph is a partial sum. First when n is 0, then when n is 1. I guess that first one didn't have a vertical asymptote, but when n is 1, it's got a vertical asymptote, the blue graph. When n is 2, still a vertical asymptote. When n is 3, 4, 5, it's not equaling the red graph. And it even has a vertical asymptote. However, it is approximating the red graph better and better when you're further away from 0. And if you play this forward, watch it here. Ready? 1, 2, 3, go. Slow it down, maybe. It is getting closer and closer to the red graph over a bigger and bigger interval. But the interval is a weird interval. It's not an interval near 0. It's an interval away from 0. But in the limit, as n goes to infinity, the partial sums do equal the function. We get equality here, except at 0. Weird. You've never seen anything like it. Gets even wilder and weirder if you allow complex number inputs into this function. And think about how the function behaves as something called a mapping of what's called the complex plane. I'm not going to explain this, but we can enjoy it anyway. This is supposed to be something called the complex plane. This is the real axis. This is the imaginary axis, but it's there. You see it. And this is a square. I'm going to let this parameter increase from 0 to 1, and we're going to see the effect of this function as a mapping of the complex plane. And it does all sorts of wild and wacky things, evidently. What in the world is going on there? I don't have time to explain it. Okay? Something weird is going on. Actually, it's not too weird if the square goes further away from the origin. If it's a smaller square further away from the origin to start with, it's not quite as weird as that. There it is. It's when you get closer and closer to the origin where the problem is, so to speak, that things get really weird. They're starting to get strange. Very pretty pictures there, though. If you ever took a class called complex analysis, you'd learn about these things. They're called mappings. Conformal mappings, in fact. And they do have applications too, for example, fluid flow. Okay. So pretty wild things. The main point is that you want to take home from this is weird things can happen. You know, we're used to simple examples of functions we're used to, and with simple examples of functions we're used to, ordinary kinds of things happen. But that's naive. There are plenty of strange functions out there that do completely unexpected things. That's the moral of the story. And as far as a true-false question on the final exam, for example, I could say, true or false, there exists a function that only equals its Taylor series at one point, for example. Would be something I could ask. And the answer would be true. Here's an example. And the series even converges for all x. The interval of convergence is all x.